Angular displacement and angular velocity. Let us consider the body in the figure which is rotating in counterclockwise direction. If we consider any two instants of time t1 and t2, the angular positions of the particle p will be given by theta1 and theta2 respectively as shown in the figure. The angles theta1 and theta2 also gives the positions of the radius vector r at t1 and t2 respectively. Therefore, r is called a position vector. The particle p is said to have undergone angular displacement from theta1 to theta2 during the time interval between t1 and t2. Therefore, the angular displacement of p is given by theta2 minus theta1 is equal to del theta, and the time interval for this is t2 minus t1 is equal to del t. The del theta and del t represent extremely small changes in theta and t respectively. The angular displacement is measured in units of radians. A radian is a pure number having no physical dimensions. The angle subtended by an arc of any length s on a circle of radius r is given by the ratio of the length of the arc to its radius, and it's expressed in radians. Let us consider again the figure where AP is an arc of length s on a circle of radius r. The arc AP subtends an angle theta at the center O. Then the angular displacement theta of p with respect to a is given by theta is equal to s by r in radians. If s is equal to 2 pi r, the angular displacement will be 2 pi r by r is equal to 2 pi radians, which is equal to 360 degrees. Let us use this unit radian to measure the angular displacement in equation of the particle p, which is said to have an angular velocity denoted by omega. The rate of angular displacement is defined as the angular velocity omega. Therefore, the angular velocity is given by omega is equal to angular displacement by time interval. Omega is equal to theta2 minus theta1 by t2 minus t1, that is equal to del theta by del t.